the fertilized egg. In this single embattled cell lie the roots of a human mind. Within hours of its fertilization, the cell begins to divide and divide again and again. Gradually, that first cell becomes a ball of hundreds of cells. They seem identical, but hidden within them is a chemical blueprint that controls what they will become. In response to some preset biological signal, the ball folds in on itself. Cells begin to assume roles, some as muscles and bone, some as heart and liver, some as part of the nervous system. A tube begins to form, the first step in the development of the brain. As the tube grows, a layer of cells appears. It's organized into neurons, which form the basis for all functions of the brain, and glial cells, which nourish the neurons and help them migrate to their destinations. They orchestrate a pattern of development that will emerge in the first stirrings of the human mind. By the 8th week, the structure of the brain has begun to emerge. On the right, a glial cell, the glue of the brain. On the left, a neuron, the future information processor. The glial cell is sending out its fibers to find the neuron, a dance that begins a major milestone in brain development.
The entire process is programmed by genes, but it is susceptible to changes in the environment. The interaction of neurons and glial cells represents a critical period of development. This is a time when the brain is most vulnerable. Teratogens, agents such as chemicals and viruses, can reach the embryo or fetus and cause harm. Recently, attention is turned toward just what those teratogens are and what kind of potentially damaging effects they exert on the brain and mind.
April 26, 1986. The nuclear reactor at Chernobyl in the Soviet Union suffers a disastrous meltdown. 10 months later, scientists estimated that mental retardation among fetuses exposed to the radiation could be 5 times as common as in the general population. They based their estimates on the results of a catastrophe that had taken place more than 40 years before. The bombs over Hiroshima and Nagasaki not only killed hundreds of thousands of people, they irradiated countless vulnerable fetuses in critical periods of development. In the wake of the bombs, clues began to emerge as to just how radiation might affect the exquisite choreography of growing brain cells.
Well, the story about radiation-related brain damage actually began here shortly after the bombings. We soon recognized that children who had been exposed in utero, a small number of them, were severely retarded. The earlier analyses of the data tended to focus on conventional division of the gestational period into trimesters. We divided the gestational period into 4 intervals of time, which correspond to more or less separable periods of development of the brain. Once this was done, it became very clear that 80%, in large measure all of the cases of mental retardation, occurred to women who were in a specific stage of their pregnancy. That is, the fetus was between 8 and 16 weeks following conception. Now, we know from neurobiological evidence that that period is extremely critical because 2 fundamental events are occurring.
First, neurons continue to proliferate at the astonishing rate of 250,000 per minute. Second, the glial cells have formed a web of fibers, and the neurons actually crawl along the web to their final destinations. For fetuses in Hiroshima, radiation interrupted that journey.
Neurons have a specific date of birth, and they'll have a specific destination. And they do not migrate haphazardly. They have an address, and they move to that address in a highly choreographed sequence of events. And since we know that brain function critically follows brain position, cells have to be in the right place to do the right thing. Even though alive, even though in the general area, they don't perform the proper function if they're not in the proper site.
Their crucial journey disrupted, the migrating neurons probably stop short of their intended destinations. These events have devastating repercussions for people whose mothers were exposed to high levels of radiation at a critical time in fetal development.
The birth and migration of neurons, two critical periods that are profoundly affected by radiation. But do other environmental insults also interfere with brain development? In 1751, William Hogarth etched Gin Lane, a portrait of despair. Among its horrors, a mother pouring liquor into a baby. Remarkably, science only began to recognize alcohol's effects on the fetus a few years ago.
Fetal alcohol syndrome was discovered by a resident in our department of pediatrics in 1970. Christy Ueland was doing a study of infants who were small for gestational age, infants who were born on term but were little. And among those children, she found a few children who looked alike, who were very small, who were all retarded, and whose mothers all had a history of heavy alcohol use.
Although the report met with skepticism, others confirmed that alcohol affected both body and brain. But what of the effect on the emerging mind? In Gothenburg, Sweden, Marita Aronson studied babies with fetal alcohol syndrome. She found that alcohol could cause damage in very subtle ways.
Many of these children have problems. They have hyperactivity, they have impulsiveness, they have temper tantrums, they have short memory span, they have perceptual disorders.
These shapes were copied by two children the same age, one normal, one with fetal alcohol syndrome. And here, a child with the syndrome who tried to draw a human figure simply couldn't stop drawing noses and eyes, a sign of damage to the frontal lobe of the brain. The behavioral effects of alcohol range from the most subtle to the most severe. But what does it actually do to the brain? In the 1970s, Sterling Claren came up on a clue.
At that time, we had the opportunity to study the first autopsied case of an infant with fetal alcohol syndrome. And we were able to get the first real visual and graphic evidence of how devastating this condition could be to the human brain. This is a picture of that first brain compared to a normal human infant brain. The first thing that's obvious is that the brain is very small. But there's more wrong with this brain than that. You can see that the gyri, which are the normal brain squiggles, are really rather flat and thick. This is a cross-section of a normal infant brain. These are the size of the ventricles, the holes in the center of the brain. And you can see how thick the white matter is and how the gyri kind of form convolutions around the brain. This is the exact same section of that brain of a child with fetal alcohol syndrome. You don't have to be a neuropathologist to see that every single part of that brain is malformed. The holes in the center are way too big because there's so little white matter to fill them in. The brain density is really reduced, and that normal convolutional pattern of the brain has been lost. We get a clue to understanding how this kind of a malformation could come about by looking at the tissue microscopically. This is a section of the cortex of the cerebrum. The normal surface of this brain is in fact here. And then there's the stuff that's covering the brain that looks like it's in fact erupting through the cortex. This is in fact a malformation. It's a hodgepodge of all the different cell lines, all the different brain elements that go into creating the brain. It's as if the cells of the brain, when they were migrating to their final homes, didn't know when to stop and continued right on through and erupted onto the surface through little bridges like these and just came up onto the surface and became scrambled. These kinds of heterotopias or cell groups that are in the wrong places are typical of fetal alcohol syndrome and would suggest that alcohol dramatically interferes with cell migrations early in brain development.
Alcohol and radiation are just two examples of teratogens. When present during critical periods of development, they can adversely affect the brain. Both kill newly emerging brain cells. During cell migration, alcohol causes neurons to continue growing past their destinations. Radiation stops them short of their target. Both interfere with the crucial timing of development.
After migration, the process of development continues. Around the 18th week, the brain begins to stabilize itself. At 21 weeks, the auditory cortex begins to function. At 26 weeks, the visual cortex links up. Witness this microcosm of normal brain development. These 3 neurons are sending out fibers trying to form a network of cells. At the end of each fiber is a growth cone, a tiny fluttering tip that depends on chemical signals to find its way. Normally, the brain produces far more neurons than it actually needs. Sometimes they succeed in linking up, sometimes they fail. For these 3 neurons, the process is simple. One of them dies. The other 2 form a connection. The scene, repeated countless times in the developing brain, leads to a network of neurons of incredible complexity. The evolution from a single fertilized egg is complete.